Good. Also, sorry about the recording of the previous class. That for some reason, I used my video editing software and it wouldn't let me merge the two videos. I have no idea, it just crashed. So I had to post two separate videos since for some reason Zoom decided to do two separate videos. I don't know why. We don't always have control over these things. Okay, so I think you know what alkenes and alkynes are. We've gone over our functional groups. You know that alkenes are hydrocarbons that contain at least one carbon-carbon double bond that, of course, are not aromatic. Remember, aromatic compounds or arenes are a different critter. We've got a whole separate chapter on those. That's chapter 4. And alkynes will have at least one carbon-carbon triple bond. And incidentally, I might as well also make this point in case you're wondering, quadruple bonds are not a thing, not in organic compounds. They might be able to occur between transition metals in certain obscure inorganic compounds. Maybe I shouldn't say obscure. My department chair at my previous school would be beating me up if he heard me talking like that about inorganic compounds. But be that as it may, you're certainly not going to find them in any organic compounds, just so you're not worried about ever running into them. Quadruple bonds for us are not going to be a thing. It'll only be single, double, and triple. And also a couple things that are worth reviewing. This is where we're going to start to talk about pi bonds. Another way of describing alkenes and alkynes is to say that they contain pi bonds. And you should have talked about sigma and pi bonds in your Gen Chem class, but it's always worth reviewing. For now, I think it's enough to say that pi bonds are something contained in double and triple bonds. That may not be a full definition, but pi bonds are a thing that you will see in double and triple bonds, not single bonds. I had an epiphany as to a way to present this material, and I just did one as a way to, I'm going to fill in that table for you guys too. So I hope I'll be able to make that clear in just a few minutes. But today we're going to talk about the structure of alkenes and alkynes, make sure we have an understanding of the hybridization of the carbons in them. And although the chapter begins with nomenclature, I'd kind of like to put that off until about, I don't know, 20 after or something like that. I want to get through the structural stuff first so we can take care of all of the nomenclature stuff all at once. Your book takes care of cis and trans alkenes in this chapter, and it talks about the E and Z business in a later chapter. And you'll notice when you look at the syllabus, I'm planning on moving up just the E and Z stuff from chapter 5 into this chapter. I think that will actually make our lives easier. I do see why the textbook authors did it this way. There is some logic to it. But the thing is that the E and Z nomenclature stuff is related to something in chapter 5 that I already know I'm not going to make you learn. So I think it makes a lot more sense to bring it up to chapter 3, where it's actually relevant to alkenes. And then when we get to chapter 5, you'll all see what that thing is. And I'll make it clear when we get to that point what you do and do not have to know. But that's why I've taken, and you can see it when you look at the syllabus, I've just taken this little piece of chapter 5 and moved it here into chapter 3, where I think it makes a lot more sense. So, but we'll take care of all the nomenclature stuff at once. And in many ways, I don't think we'll have to go through quite as many or quite as much, because if you know how to name alkanes, you've got like 90% of what you need to know to name alkenes and alkynes, if not more. So let's talk a little bit about bonding in alkenes and alkynes, where, as we've said, and as you already know, we have multiple bonds between carbon atoms. First thing to be aware of is that single bonds, double bonds, and triple bonds are not created equal. They're very different from one another. As we go from single to double to triple bonds, the term we use, we say the bond order increases. So a double bond has a higher bond order than a single bond. A triple bond, a higher bond order than either a double bond or a single bond. That's probably a term you learned in Gen Chem. And in fact, I bet you also learned in Gen Chem that as the bond order increases, the strength of the bond increases. Other things being equal, by the way. No fair changing elements around. But we want to make sure we're comparing apples to apples in as much as we possibly can. So a double bond is stronger than a single bond. A triple bond is stronger than either a double bond or a single bond. Again, other things being equal. And the opposite is true of bond length. As you go from single bond to double bond to triple bond, the bonds get shorter. And again, I don't want to, never mind, I won't go into all that. But I thought this occurred to me as a way of presenting that information in a nice pictorial way, if that's a word. So I'm not generally a huge fan of memorizing pictures. I think it's a trap. One of my deeply held beliefs is that we tend to think we're learning something when all we're doing is memorizing a picture. And memorizing a picture may be fine, but it's not the same thing as learning something. So you'll get a chance to apply all these ideas in the OWL assignment. And again, I've also made some questions from past exams available on Canvas. So you're able to look that up. Just a reminder on that, by the way, I know I've already said this, but a second time doesn't hurt. Remember that the study guides that I put on Canvas are not necessarily broken down by exam. In other words, it's not the first one is for the first exam, the second one is for the second exam, third one, not necessarily. Particularly since we also have 2 new chapters this term that I don't have any material yet to share with you. Meaning I don't have any questions from past exams because I've never made any questions on them before. So, but they are broken down by chapter, and you'll be able to see examples of questions from each chapter. It's just for any one given exam, you may have to refer to multiple study guides in order to get, depending on how the exams are broken down, in order to see examples of questions from that chapter. I'm certainly not going to give out all the questions and answers ahead of time. I have to have some standards. You know, like I say, this is a university course. But I think it's reasonable for you to ask me to give you a few questions, some questions. That's not an unreasonable thing to ask for. So that's what I've done. I've given you some examples of questions from old exams, just to give you an idea of what to expect. I'll also say it again, I'm planning on 60 questions for the first exam. I think they'll in general be around 60 questions. Final exam, probably more because you have 2 whole hours. So I don't know, that might be 80 or 90, but in general, you can expect, I can tell you this much, there certainly will not be 100 questions, if that's what you are worried about. We only have about 50, 55 minutes, so there's a limit to how many I can ask. The smart people all tell me no more than 30 seconds to a minute per question, so, so I think 60 is reasonable. Good, I think that's all I need to say about that. Back to single, double, and triple bonds. Now, where does sigma and pi bonds come into all this? And again, I think you probably had this in Gen Chem, but it doesn't hurt to review it. Please be aware that a single bond is a sigma bond, period, full stop. So every single bond contains 1 sigma bond, no exceptions, and 0 pi bonds. A double bond will contain 1 sigma bond and 1 pi bond. A triple bond will contain 1 sigma bond and 2 pi bonds. So I certainly hope that your Gen Chem professor told you those things, as opposed to other things that are not true. So I do worry sometimes. But be that as it may, these are always going to be the case. You can depend on those definitions. There are no exceptions. Every single bond is always a sigma bond, no exceptions. Every double bond, regardless of what 2 atoms it's between, will be a sigma bond and a pi bond, no exceptions. I've learned over the years that students like those words, no exceptions. So I use them whenever I possibly can. And a triple bond is 1 sigma and 2 pi, no exceptions. That's always going to be the case. And I mean, to get into a full understanding of the nature of a sigma bond and a pi bond in molecular orbital theory, I can't think of any possible earthly good that would do you guys. But they are called these things for historical reasons. The connection from sigma and pi is to S and P, as you might have guessed, because sigma bonds often involve S orbitals, not always, but often. And pi bonds much more generally involve P orbitals. At least I think you'll in general find that to be the case. There are other types of sigma bonds as well, but I'm hard pressed to think of a pi bond that doesn't involve p orbitals at some level. And I think you talked about sp and d orbitals in Gen Chem. So that's where those terms come from. But I think going much deeper than that, I can't come up with any decent reason to go any deeper than that. I don't think it's worth your time. Good. So we already talked about the formula of an acyclic saturated hydrocarbon. So that's another thing worth reviewing. CnH2n+2, another way of looking at that, another way of thinking about that, is that if you have a compound with n carbon atoms in it, the most hydrogens you can have is 2n+2. You can't have any more than that. That's the maximum number. That's why we call compounds like that saturated, meaning saturated with hydrogen. They contain the absolute maximum number of hydrogen atoms possible. And we've also said every 2 hydrogens you lose means you have either a ring or a multiple bond. You don't know which, but it has to be one of the 2. And I think we've already talked about this. Remember, I said that this means that when you have a molecular formula, there are limits on the structure of what that molecule, of what the structure of that molecule can be. And just as there are limits on molecular formulas, right? A molecular formula can't be absolutely anything, right? CH6 is impossible. See what I mean? So there are limits on these things. There's not an well, there may be an infinite variety when you go out to an infinite number of carbons, but for any given number of carbon atoms, let's say, there's not an infinite variety of formulas and not an infinite variety of structures. It's limited. Of course, as the number of carbons gets large, the number of possible structures, or the number of isomers, you might say, gets extremely large, and it does get very large very quickly. By the time you get up to 6, 7, 8 carbons, you're looking at hundreds of thousands of structures, maybe even millions that are possible. So there's a lot of possibilities, but not an infinite number of possibilities. Good, so I think that's all I need to say about that. Let me see if there's anything else. Another thing I should say about double and triple bonds that's important to be aware of. You know, just the other day we talked about rotating around single bonds. That's a possible thing, unless of course there's a ring. You're not going to break the ring open. But certainly in acyclic compounds in general, you have full freedom of rotation around single bonds. That is not true for double or triple bonds. I don't mean to wave my finger at you, but that's not true for double and triple bonds. You cannot rotate freely around a double or a triple bond, at least not at room temperature. So let me write that down for you. Cannot rotate freely around double or triple bonds. And again, it doesn't matter which atoms the double bond or triple bonds are between. You can rotate freely around single bonds in general. Again, unless there's like a ring or something like that. Then you have limits on how far you can rotate. You can do those ring flips, those chair interconversions in cyclohexane. You can't turn all 360 degrees or you'd be breaking the ring. But certainly in the absence of a ring or something like that, you have full freedom of rotation in most cases. Maybe I can't say all, but in most cases. So that's something important to be aware of. That means that we're going to have options, especially when it comes to double bonds. That's where cis and trans alkenes come in, and also E and Z alkenes. So that's something to be aware of in terms of the structure of alkenes and alkynes. Let's see. I think all I would like to do before we get into nomenclature is I want to relate all this to hybridization and make sure that we're all clear on that. So maybe I lied a little bit before. There is some review even here in chapter 3 from Gen Chem, but that's okay. I don't mind that at all. I think it's perfectly reasonable. You know, it ought to be good news. It means something you learned in Gen Chem actually turned out to be useful later on. So there you go. You got to use it again. It's not a bad thing at all. Good. So we already said that a double bond is a sigma plus a pi, and a triple bond is a sigma and 2 pi bonds. So let's make sure that we understand hybridizations. There's really only 3 that I think you're going to have to worry about: Sp3, Sp2, and Sp. You're not going to need any of these exotic ones like D2, Sp3. Again, those apply to metal complexes. If we were in an inorganic chemistry class, we might need those. Here, we're not going to involve d orbitals. So basically, Sp3 hybridization is going to involve, certainly for carbon, Sp3 hybridized carbon will have 4 single bonds. And other atoms can be sp3 hybridized also. An oxygen that's sp3 hybridized, though, will not have 4 bonds, right? Because oxygen likes to have 2 bonds. So instead, it will have 2 single bonds and 2 lone pairs. That would also be sp3 hybridized. So other atoms can also have these hybridizations. But since we're going to be mainly looking at carbon, we can certainly focus on carbon. In an sp2 hybridized carbon, what you will find is that there's 1 double bond and 2 single bonds. I mean, at least for sure, we're talking about carbons that have a formal charge of 0. You can get these hybridizations in things like carbocations. We'll learn more about that later. But certainly if you're talking about carbon, and certainly if you're talking about a formal charge of 0, these are going to be the hybridizations that we'll find. These are the hybridizations that are required for the molecule or for that carbon atom to be able to have those kind of bonds and to have the correct molecular shape. I'm hoping in Gen Chem, you connected hybridization to molecular shape, and those things are still important. Hopefully you learned that the sp3 hybridization is connected to a tetrahedral shape. And so anything that's sp3 hybridized are going to have the 4 regions of electron density around them, whether they're bonds or lone pairs, be in the shape of a regular tetrahedron. And likewise, oh, heck, why not put that down? How would that do anyone any harm? So we associate the tetrahedral shape with sp3 hybridization. 2 single bonds, 1 double bond. And also we associate the shape trigonal planar, planar triangular. Basically, the shape of an sp2 hybridized atom is going to be that of an equilateral triangle. And again, I don't think you're going to find any exceptions. I'm certainly struggling to come up with one. I doubt there are any. And then last but not least, if you've got an sp hybridized carbon, at least one with a formal charge of 0, you've got 2 options. You've got either 2 double bonds coming off the same carbon, or 1 single bond, 1 triple bond. And the shape that we associate with that is linear. So in order to have that linear geometry, the carbon atom must be sp hybridized. And you can see already why we call them pi bonds. If it's sp hybridized as opposed to sp3, those 2 p orbitals must have gone somewhere. And where they've gone actually is nowhere. They're still there. They're just not included in the hybridization. And it's those that we use to make the multiple bonds, the pi bonds. So that's why p and pi kind of go together. Whereas the sigma bonds use other kinds of orbitals. Good, or other orbitals that are involved in the hybridization. Good, and I think that's all I need to say about that. I'm comfortable saying there's no exceptions. I don't think you'll find any. If you think you found one, I'd like to know about it, but I don't think you'll find it. Again, certainly as long as we're talking about carbon, and as long as we're talking about carbon with a 0 formal charge. We'll talk a little bit about charged carbon species, carbocations and carbanions. Those do exist, and we'll get to them eventually. We'll talk about them a little. I don't think we're going to talk about them a huge amount, but we'll talk about them a little. Good, so let's do some examples so you can see how all this works out. The simplest possible alkene is ethylene. We've already talked about it a little. I guess your IUPAC name would be ethene. Instead of ethane, it would be ethene. But no one really calls it that. Everyone calls it ethylene. So both of these carbon atoms we know are sp2 hybridized because they fit the definition. They have 2 single bonds and 1 double bond. If instead you had, let's say, cyclohexene, alkenes can be cyclic. Then the 2 alkene carbons will be sp2 hybridized, and any of the other carbons will be sp3 hybridized because they're involved. So all 4 of the other carbons are sp3 hybridized. They're involved in 4 single bonds. Each of those carbons has 2 single bonds to carbon and 2 single bonds to hydrogen. Remember, any Any valences that you don't show in a line angle drawing are assumed to be to hydrogen. So those will all be Sp3 hybridized. What about a molecule like acetone? Being careful to draw our lone pair electrons. Well, the carbons in the methyl group will be Sp3 as usual. The carbon involved in the double bond to oxygen will be Sp2 hybridized, and in fact, so will the oxygen also be Sp2 hybridized. It has to be in order to accommodate the double bond. So instead of 2 single bonds in a double bond, it is 2 lone pairs in a double bond. But that oxygen will still be Sp2 hybridized. What about a molecule like this one? We'll learn today that molecule is called 3-hexyne. And I expect you'll be able to come up with names like that. It doesn't have to be today, but you'll get to practice coming up with those names in the Chapter 3 OWL assignment. And I'm expecting that by the end, I'm hoping at least that by the end of this lecture, that'll be something you'll have already seen a couple times. So in this case, the carbons in the CH3 and CH2 groups will be Sp3 hybridized, and the carbons involved in the triple bond will be Sp hybridized. What about a molecule that has 2 double bonds on carbon? Molecules like that exist. One that you're familiar with is carbon dioxide, in which you'll find that the 2 oxygens are Sp2 hybridized, and that central carbon, the one involved in both double bonds, is Sp hybridized. The fancy term we use for 2 double bonds coming off the same atom, there's a fancy word. They're called cumulated double bonds. I don't know if I really care that you know that, but in case you're curious, that's what they're called, cumulated double bonds. There are other types of double bonds too, but that's what we call it when they're coming off the same atom like that. There are other atoms, certainly, or other molecules, certainly, that have cumulated double bonds. It's not something you run into a lot, but you will run into it occasionally. What about something like this? So now we have 2 carbon atoms. Both of these on the end are going to be Sp2 hybridized because they have 2 single bonds and 1 double bond. But once again, that carbon atom in the middle is Sp hybridized, and we'll have a linear geometry. Have to have Sp hybridization to be linear. And you have to be linear to be Sp2 hybridized also. So that goes both ways, actually. So this is, I think, some helpful background in terms of the structure of alkenes and alkynes and the hybridization. The reason I'm mentioning all that is I'm going to be using these terms as we go. I'm going to be talking about Sp and Sp2 hybridized carbons. I'm going to be talking about single and double and triple bonds, and we'll expect you guys to know how they vary in bond order, bond length, and bond strength. That's part of understanding the bonding and understanding where sigma and pi bonds are found. We don't need to go into full detail about what they look like, and it's this much along the internuclear axis, and so on and so on. I don't think that's worth our time. But I think at least this much that you see here, which again, if you're watching the YouTube video, you can stop the video here, and if you missed anything, you can always get it later. I mean, I also don't want to be like that guy. Have you guys had a professor like this? I did when I was in college. He was a math professor, and he literally, not even exaggerating, was chalk in one hand and eraser in the other. And literally, so I really don't want to be that guy. But luckily we have, back then we didn't have YouTube or any of the modern technology. So today we do have the technology. We might as well take advantage of it. Good. Any questions so far then? Just let me find my cursor first. You mean I did it again? I'm such a good teacher, and that was so clear that no questions are even possible. In my dreams, I wish that were true. That's good, though. I'm just teasing you. Okay, well, I think we can then spend the rest of the time on alkene nomenclature and also get into cis and trans alkenes, which are discussed in this chapter. And as you'll imagine, there is kind of a conceptual link between cis and trans and alkenes and cis and trans and cycloalkanes, which we've already covered. But then I think it's better for us to move the E and Z thing forward to this chapter. So again, please consult the syllabus. It will say what you need to know for the exam. Good. So in terms of nomenclature of alkenes, and alkynes, if you can name one, you can name the other. Whoops, alkynes, there's a K in here. Happily, I can tell you if it's really just like naming alkanes, except you also have to say where the double bond is or where the triple bond is. So if you had something like this compound, then we'll start with a small one. Then you need to say where the double bond is. And you also need to include the carbons that are involved in the double bond in the main carbon chain. So I think our main carbon chain is going to look like this, 1, 2, 3. So we're going to name it after propane in some way. But we also need to remember, since it's an alkene, that the name is going to end in -ene rather than an -ane. So I would call this compound 2-methyl propene. Or if you wanted to be a stickler, you could call it 2-methyl 1-propene, but it really is the only possible place you can put the double bond. So I think both those names are correct. And if you don't like that first name, you can certainly use the second name. It's perfectly fine. The reason I know to call it that is because the double bond is between carbons 1 and 2. And it starts at carbon 1. And then over here, also attached to carbon 2, we have this methyl group. So we need to name it as such. That's the methyl in 2-methyl 1-propene. So that's a fairly straightforward one, but I wanted to start with something pretty small. Let's go a little crazier. Let's do a cyclic one. That's a good one. So the 5-membered ring, if it were just a saturated 5-membered ring, we'd call it cyclopentane. This is going to be something with cyclopentene. But we need to say where the double bond is, and we need also to say where any substituents are. So it's best practice, I think, to start the double bond at carbon 1. I certainly always try my best to do so, and have it go through carbons 1 and 2. So then we'll see that our ethyl group, that's an ethyl group over there, is on carbon 3. And so I think that's the best name. 3-ethyl cyclopentene. And 1-cyclopentene is understood. Once again, I think it wouldn't be wrong to say 3-ethyl 1-cyclopentene, but people will often leave that out because it's understood. If the alkene is at carbon 1, that's what that then, and you leave that number out, then that's going to be understood, just as it was in 2-methyl propene. So I think that's the best name for this. So again, what you need to know is that when you're naming an alkene, you need to state where the alkene double bond starts, or if it's an alkyne, where the alkyne triple bond starts. In cyclic alkenes, it's best if you can start the double bond at carbon 1, make it between carbons 1 and 2, if at all possible. If not, then you'll apply the same rules to naming alkanes in terms of knowing what to number everything. And then you'll also number all the substituents and state where they are and what the substituents are. I would say well, let me just say this one thing before I forget, because I'm likely to forget, then I'll get to your question. What I want to talk about is what it means to know this material and how to study for the exam of this material. So I would say what you should aim for is to be given not just an alkane, but an alkene or an alkyne that you've never seen before, and come up with the correct name. The way you do that is by practicing with problems in the book, by practicing with OWL questions. On a similar subject, I wish we had a TA or an SI person to do review sessions with you guys, but we don't. Some of you have asked me about that. Unfortunately, no, I'm it. It's all me. So I'm available in office hours to help in any way I can. Sorry. If at all possible. The only reason it might not be possible is if you're trying to come up with the lowest possible sum of all the numbers. Oh yeah, well, naming cycloalkanes, there's a couple different ways to do it. I expect carbon 1 is going to have something attached to it. And then you, well, let's do one. Oh, let's go crazy. How about that? So you know you want a number starting either 1, 2, 3 or 1, 2, 3. And if you don't know which, you try it both ways. And you use the lowest possible sum. If that still doesn't work, and we gave an example like this in class, then you go by alphabetical priority. So you've got E for ethyl group and M for methyl group. So the E wins. So I think this would best be called 1-ethyl, oh, cis-1-ethyl, 3-methyl. No, I guess I do need a hyphen in there, 3-methyl cyclohexane. But I believe that if you apply the step-by-step rules that are in the class notes, you will always be able to find the best possible name. I sincerely do believe that. But I feel I've still not answered your question. How should I change the structure? Oh, okay. Or is that one okay? Okay. Oh, yeah, I see what you mean. I think it would be the best idea to make carbon 1 of something attached. Yeah, and then that will probably limit it to 2 possibilities. You want either the lowest possible sum or you'll go by alphabetical priority. But I think that will in general work. Yep, no, you're fine. Let's see. So I want to do some more examples of alkenes and alkynes though. Oh yes, I'm sorry, you had a question too. That's for acyclic ones. So that's not true for rings. Well, remember when you find the longest chain, you're not allowed to lift your pencil off the paper. You can't go 1, 2, 3, 4. So well, but if you did, then you'd have 3-methylpropene and the numbers would be higher. Or you'd have like you would have 2-methyl-2-propene or something like that. And the numbers would be higher. So that's how I knew to make this carbon 1. You're saying to start numbering over here. No. You want to start numbering here. Like that? Oh, you want to go 1, 2, 3. Okay, well, if you do that, then the double bond isn't contained in the chain. So you want yeah. I mean, are there ways of dealing with it? If it's not, yes, but I would avoid that if at all possible. I think you'll find it's always possible to include it. And actually on that note, I was going to do something with 2 double bonds. So now you're going to want to include both of them. So let's name this one. I think we should start numbering over here because that will get us closer to the methyl group that's attached. It looks to me like the double bonds start at carbon 1 and carbon 3. Those are where the 2 double bonds are located. The chain is a 4-carbon chain, so we'll name it after butane. So it's not going to be butene, it's going to be butadiene, 2 double bonds. And then we want to say that carbon 2 has a methyl group on it. So we'll start with that, 2-methyl, 1,3-butadiene. And I will also just let you know, there is another way to do this too that's also correct. You can actually put the numbers before diene. You could also call this 2-methyl-buta-1,3-diene. That's how they do it in Europe. In America, we usually name them this way. I don't really care which way you use. I think this way might be a little clearer. But just so you know, in case you might see it mentioned in an OWL problem, that other way is also correct. It's equally correct. Neither of the two is any better than the other. They're equally correct. I'm kind of a fan of doing it like this. And I find generally students are too, if they had to pick one way over the other. Make sense? Questions on that one? Yes. But why wouldn't it what? Die what? Oh, you need to put the di before the ene because you're saying there's two of these, two enes, two double bonds. Is that what you meant? Yeah, not dibutene, not dibutene, but butadiene. Otherwise, it sounds like there's two butyls or something. I see I'm not convincing you. So dibutene makes more sense to you. Or you're just asking. Okay, that's fine. I think the reason they put it here is so that the di that means two is closer to the ene. It makes it look a little bit clearer that there's two enes, two double bonds. I've never been asked that question before. It's a perfectly good question. But that, I think, is the reason. Other questions then? The poor people that are behind me. I know I always say it. Okay. I think I have at least one more. I'd like to do an alkyne if we can. What about? Hard to write with an eraser, isn't it? Doesn't look so good. What about this compound? Well, again, you want to start numbering closer to where your double bond is, if at all possible. So I think we'll call that carbon 1. Remember, we don't number the hydrogen. The hydrogens are included in the chain. 1, 2, 3, 4, 5. So it's going to be some kind of pentyne. And looks like the triple bond is on carbon 1. It's between carbons 1 and 2. So you always say where the multiple bond starts. Which carbon does it start on? If it's between these two carbons, which is the first carbon that includes the multiple bond? And I think you'll agree that's carbon 1. So I think we should call that guy 1-pentyne. YNE. Looks funny, but that's the correct name. So you name alkynes just like you name alkenes, except alkynes are easier because you don't have to worry about any of this cis-trans stuff, which is what we're going to spend the rest of the class on, cis-trans and EZ. Because in the examples I've given, I've carefully managed to avoid a further issue that you have with alkenes. Not with alkynes, but with alkenes. Further issue with alkenes. I'm just trying to write down everything I say because I've listened to student comments and I hope I understand student concerns. Further issue with alkenes and alkynes. I'm really trying my best here. You will notice that there's two different 2-butenes. And those two are different compounds. Remember, we said a while ago, you cannot rotate around a double bond. You can around a single bond, but not around a double bond. So those two are isomers. In fact, they're a type of stereoisomer, which is a term that we've defined. But those are different compounds, so we can't call them both 2-butene. They need two different names. And just as with cycloalkanes, cis referred to two groups on different carbons that are on the same side, and trans referred to two groups on different carbons that are on opposite sides, the same thing is true here. We call this one trans 2-butene, and this one cis 2-butene. So that's how we distinguish them. The other isomer of butene actually looks like this. And with this one, we're not going to use cis or trans. There's no cis and trans distinction. Cis and trans only works if on each of the alkene carbons, you have two different things. Do you see how on this carbon, there's an H and a CH3? And on this carbon, there's an H and a CH3. They need to be both different in order to have a distinction. So here, the two larger groups The two methyl groups are on opposite sides. So that's why we call it trans-2-butene. Here they're on the same side. The two larger groups are on the same side. So that makes it cis. By side, I mean on the same side of the double bond. So if you need a visual aid, you can draw a dotted line going right down the double bond. And that might help you to see it a little better. That will give you a visual aid. Same thing over here. The two larger groups are on opposite sides of the double bond. Draw a dotted line down the double bond if it helps you to see. We don't have that with this one. There's two H's on this carbon and two CH3s on that carbon. So there is no cis and trans. And that we have that one already. That guy is just 2-methylpropene. Wait a minute. Yeah. Yes. It's the same as the compound we did before. Thought I was losing my mind for a moment. Yes. Let's see. These two are stereoisomers. And this one is a constitutional isomer of both. And I don't have time to go over the definitions of all this again just now, but if you look at the definitions, you'll see they fit the definitions. Yes. Why is it not 1-dimethyl? Because we'll start numbering from the double bond. And because the other methyl group is part of the chain. That's right. Yeah, so it's 2-methyl, not 2-dimethyl. Yes. Oh, well, again, you want to go 1, 2, 3. And the reason we don't do that is then the double bond isn't in the chain. You want to go 1, 2, 3? No, it's okay. Oh, you got it? Just want to make sure. Okay. So that's fine. So there's just one other issue I want to go over, which is the thing I'm taking from chapter 5. And it says in the syllabus where it is. It's just that one little topic on E and Z. And the reason is, if I only told you about cis and trans, I'd kind of be lying by omission. I'd be only telling you part of the story, because it's very easy to break the cis-trans system. And I'll show you what I mean. Where's my trash can? There. I'll show you what I mean with an example. Oh, we already did 3-hexyne, so we've done an example of an alkyne. Let's look at, I hate that example. I'm going to make up a different example. Woohoo. Let's look at this compound. So we've got a problem, because now there's 3 things that are not H's, not just 2. So are you going to say that double bond is cis, or are you going to say it's trans? It doesn't work. So we need another way to deal with situations like this. And that's where this E and Z system comes in. So what you do is you look at each of the 2 carbons, and you can draw a dotted line down the alkene carbon if you want to. That helps you to see better. But we're going to deal with each of the groups separately. First one carbon and then the other. And what we're going to do is compare these 2 things that are attached to that carbon. I think you'll agree it's a chlorine and a carbon attached to this carbon, right? We have a chlorine over here and a carbon over here. And we'll ask simply, which of those 2 is heavier? Which has a higher atomic number or a higher atomic mass? You'll get the same answer. And I think you'll agree chlorine is a higher atomic number. So this one wins. That's going to get priority 1. And the methyl is going to get priority 2. Again, I want to be sure that I'm clear. I'm talking about the groups that are attached to this carbon right now. And I think you'll agree that we have a chlorine over here and a carbon over here attached to that carbon. And that's what we'll do. We'll just give them priorities based on the atomic number of that element. And then we're going to do the same thing over here. Now we're going to be looking at this carbon. And we're going to look and see what's attached. And I think you'll agree that over here, we've got a carbon attached. And over here, we've got a hydrogen attached. Do you see how there's an H attached to this C and another C attached to this C? Everyone see what I'm pointing out here? So I think you'll agree in terms of atomic number, the carbon wins. It has priority 1. And the H has priority 2. And that's all you need to do in order to be able to decide whether the double bond is E or Z. And we'll call the double bond E if let me see now. If the priority 1 groups are on opposite side of the double bond, and you can tell which side they're on again by drawing a dotted line down the double bond, if you find that makes it easier to see. And we'll assign Z if the priority 1 groups are on the same side. And if by chance, as I did way back when I was in school, you took German when you were in school or spoke it at home, you just won the internet, because that's where these come from. E comes from the German word entgegen, which means over yonder on the opposite side. And Z comes from the German word zusammen, which means together. If you did not take German, then the way they usually have people memorize it is Z is for same side, which is as stupid as it comes, but it works. So those are how you define that. So all we'll do is we'll name the compound just like we always would. Let me see here. I think we're going to start numbering over here. And again, the reason I don't put the double bond on carbon 1 is I can't. It's not on the end of the chain. So we'll start numbering closer to the double bond. Let me draw it again. I'll name this and then you can go. So that's how I'm going to number the carbons. The double bond is going to be between carbons 2 and 3. I'll even take some notes. Between carbon 2 and carbon 3. And then we have a chlorine at carbon 2 and a chlorine at carbon 4. Right? Can you see how they're attached to carbon 2 and carbon 4? So we'll say that we have 2 pentene, since the double bond starts at carbon 2, and we'll say that we have chloro groups at carbons 2 and 4. So I would call this, we also saw that the 2 priority 1 groups are on the same side. So we're going to call this Z. And I think we would want to call this something like Z 2,4-dichloro 2-pentene. We have to go with E and Z here because we can't use cis and trans. I'll tell you what, I'll start Monday's class with this. I'll go over in detail how you can know how to name that. But we'll end with that. So have a great weekend. I will see you all on Monday. Just like with Cycloalkanes. No, I've already made the change. Do you have to? Yes, because I had a color wheel. And then it's obvious it's supposed to try to do it's obvious where this is going, but that's it. Sunday the rest of the Same thing with over here. There's all, that's because they're the same. But here or over here, it does exist, but it's the same. They're the same as those two, yes. And the way you know that is by naming the compound. You'll see they have the same name. It's not that it doesn't exist, it's that it's the same. They can be tricky, but that's how you do it. You just write out all the possibilities, and then you see if there's differences. So that's part of knowing whether it's the same isomers. We are checking all of the connections. If all the bonds are the same types, then they're the same compound. But if you don't like that method, another way is to name the compound. Come up with the same name. I know those. Well, the thing is, the way it's drawn right there, they're not really distinguished between compounds. The way you tell that is because there's no wedge or dot on it. They're not making any distinction. They're not even calling attention to that meaning. But again, the way you can tell they're distinct is I'll look at the same name. Sure. Susanna, yes. Entgegen. You know German, yes. Entgegen. Entgegen. Yes. No, those are not different conformations. And the way you know that is up and mass down, because these are both up.